So with that, it's my pleasure to introduce our first speaker, Evangelia. Evangelia holds a PhD in clinical prediction modeling from KU Leuven, with a background in mathematics and biostatistics. She is now a postdoctoral researcher at the German Cancer Research Center, or GKFZ, in Heidelberg. Her work focuses on the validation of AI methods in biomedical imaging, with a particular emphasis on performance uncertainty and dataset size effects. Evangelia, the floor is yours.
Thank you so much for the kind introduction and the invitation. Let me share my screen. I believe that you can now see my... Okay,
Yeah.
perfect. I'm happy for that. Good afternoon, everyone. I'm very excited to take part in this seminar, and I hope my talk will spark some interesting discussions. It is titled From Metrics to Meaning, Making Evaluation Matter in Medical Imaging AI. And I would think it can serve as an opportunity to explore the current state of the art when it comes to performance reporting of medical AI algorithms, sequentially discuss how bad practices can be prohibited in the community, and explore how a reliable medical imaging AI future should look like. It is often the case that when we think about an AI developer's work, we primarily focus on the output of their work, which is the machine learning algorithm. However, there are so many incredibly important aspects that relate to the reliability of the algorithm that often do not get to be considered. Today, my talk will be centered around performance reporting, and I will also be exploring the stability of rankings in medical imaging AI papers. When it comes to successes of AI in medicine, it seems that medical imaging, represented by the field of radiology, presents with a majority of FDA-approved devices, demonstrating in this way a strong potential for clinical translation of such applications. And as the number of FDA-approved devices is rising over the years, it seems that it is important to note that based on a commentary published recently, or 2 years ago, in Nature Medicine, there is very limited clinical validation of these AI devices. In fact, the article is stating that only 4% of those were supported by randomized clinical trials, which is the strongest experimental evidence standard in the field of medicine, and 40% of them lacked any published clinical validation data. In an effort to investigate reasons for the failure of clinical translation of these devices, by taking a look at the common picture of medical imaging AI publications, where often a new method is getting proposed and its results are presented in tables where this method is compared to previously introduced state-of-the-art methods with a minimal margin of performance increase. And as some sort of self-fulfilling prophecy, the new method outperforms the rest on the basis of mean performance metric values alone, without any reporting of model performance variability. And this so-called state-of-the-art chasing is prevalent also in the leaderboards of platforms that are hosting challenges like Kaggle. Here I'm pasting a couple of screenshots of leaderboards of medical AI challenges on Kaggle, and you can see that the ranks are determined by using only one common performance metric alone, without any reporting of model performance variability. And high performance variability is something that one would expect in the medical imaging AI domain, since these datasets in this domain are often small compared to the general vision datasets, have high heterogeneity, and there is a lot of noise present in them. But before moving into the topic of performance variability reporting, I would first briefly go about one important aspect for the validation of AI algorithms, which is the choice of the right performance metric. There are so many metrics out there. A lot of them have their pros and a lot of them have their cons. And a couple of years ago, when we went around in the challenge participant community, most of the times the motivation for selecting a metric was what is currently widely used or what is most commonly used in a certain community. And when it came to classification tasks, accuracy was the most often selected metric, while for segmentation, the dissimilarity coefficient and the Hausdorff distance were the most frequently selected. But now let us see whether selecting the most widely used metric is always a good idea for evaluating an AI model. Imagine that we have this toy example where we would like to demonstrate the effect of class imbalance. So we have one data set that comprises of only 3 sick individuals, and our aim would be to use an algorithm that would be classifying patients into the sick or the healthy class. And exemplary, the output of this algorithm is the following, where all patients get to be classified into the healthy class. If we were to use standard metrics like accuracy, we would have a very misleading picture that relates to the performance of the algorithm, while when using a metric that is actually accounting for class imbalance, balanced accuracy, we would have a completely different picture. But is balanced accuracy always the right choice? Imagine that we have another example like the one that you see pasted on this slide. We have a confusion matrix where the false positives are severely overrepresented. If we were to use accuracy or balanced accuracy, again, we would have a very misleading picture that would relate to the performance of a certain algorithm. When considering, though, metrics that account for predictive values, like the positive predictive value or the Matthews correlation coefficient, we get to obtain a completely different picture. Now, I will also demonstrate some motivating example that would raise awareness with regards to problems that arise from not selecting the appropriate metric for the problem that we have at hand. Imagine that we have a problem that relates to object detections, and we have this reference image from colonoscopy, and we would ideally want to use an algorithm that would detect all 3 polyps present in the image. We use 2 algorithms. One of them is detecting one of the 3 objects, and the other one is detecting all 3 objects. If we were to use a standard metric for segmentation, like the dissimilarity coefficient, we would again lead ourselves to be misled because algorithm 1 seems to be outperforming algorithm 2, even though it misses out on the small polyps that can have, which is something that can have detrimental effects for a patient's health if we miss out on smaller polyps that could potentially grow. In this way, we try to uncover several problems that relate to the selection of the incorrect metric. And beyond uncovering such problems, we also wanted to solve them. And for this reason, we established the Metrics Reloaded Consortium, where the motivation was to provide researchers with a comprehensive framework for metric recommendations. This framework was based on the so-called problem fingerprinting. And essentially, the researcher or the user of the framework would be asked certain questions that relate to the problem that they have at hand. For example, whether structure boundaries are particularly important for the problem that they have, whether there is high variability of structure sizes. And in this way, the properties of the problem get to be captured in a structured manner, and we call this the so-called problem fingerprint. We tried to account for multiple classification scales ranging from classifying at a whole image level to increased granularity of classification up to semantic segmentation. And with this framework, we also tried to incorporate recommendations that can be applied in a wide variety of modalities, ranging from computed tomography, microscopy, endoscopy, and so on and so forth. The resulting framework looks quite daunting at first, but the colored lines can be used as visual aids for a certain pathway that one can follow in the framework. For example, let us consider the case where we went about the problem fingerprinting questions, and the problem category that resulted from this fingerprinting was image level classification. Then we would go about following the blue arrow and answer more specific questions that would narrow down the metric candidates for the problem that we have at hand. And in the end, we would obtain a list of appropriate metrics for the evaluation of our problem. We always get to obtain a list because no metric is standalone. Because as I mentioned before, each metric is in a position to capture certain properties of the predictive capabilities, performance capabilities of one algorithm. And because there are so many metrics out there, we did our best to make those metric recommendations as accessible as possible to the community. So we created the so-called metric cheat sheets where one researcher could search for a certain metric and obtain its functional form in a cheat sheet, certain properties that are very important for the metric and relevant pitfalls. We also went about a standard Python implementation because across Python libraries, the metrics tend to have smaller deviations in the results that we get to obtain from them. And given the fact that there are so many metrics out there, as mentioned before, and a lot of them are synonymous or can be mutually computed from one another, this heat map can also give a good understanding of how the metrics relate to one another. And we went even one step further by introducing a toolkit, an online toolkit that can guide the user in selecting the appropriate set of metrics. Here you can see examples of questions that would lead one to obtain the problem fingerprint of their problem that they have at hand. And in the end user is obtaining a metric list that is recommended for their problem in a PDF file. And as I mentioned previously, the second part of my talk will be focused around the reporting or good practices for reporting model performance, because it's important, of course, to select the appropriate metrics, but then the step further would be to also demonstrate how stable model performance is. When looking at papers in medical imaging AI, I demonstrated even previously these commonly encountered results tables. And these tables, as I mentioned, are only focused on the mean performance metric values alone, without any reporting for performance variability, which is something that is at odds with guidelines from regulatory agencies. Here, for example, we see guidance from people that work at FDA, and there they recommend that all performance estimates should be provided with confidence intervals. And this is something essential for clinical translation. 2 years ago, we tried to conduct a systematic analysis of the MICCAI 2023 segmentation papers when focusing on extracting performance variability related data from them. And we had 3 central questions. I'm not going to go too much into detail into the questions, but I think the results speak for themselves. So for the segmentation papers of MICCAI 2023, more than 50% did not report any variability. Out of those papers that actually did report any means of performance variability, only 1% of them reported confidence intervals. And out of those papers that actually reported standard deviation of model performance, in the vast majority of those cases, been computed. And focusing on the papers that did not report standard deviation in this study, we decided to consider an approach to approximate it and use the approximated values to reconstruct confidence intervals of the target metric. Our assumption is that a wide confidence interval demonstrates unstable model performance, while a narrow confidence interval is desired for better potential for clinical translation of one algorithm. Without again not going too much into detail of this previous of the results of this previous study, this exemplary forest plot-like graph has these vertical red lines that are basically indicating the cases in which we observed that the mean performance metric value of the second ranked paper in a a second rank method in a paper was within the confidence interval of the first rank method. And this is something that we observed to be happening in more than 60% of the analyzed papers. And with this motivation, we wanted to further explore the stability of rankings of those methods. And we essentially wanted to answer, or at least provide one with one intuition or a formula with which they could estimate how likely it would be that such rankings would flip. And to answer this question, at the first stage, we again extracted data from MICCAI 2023, and this time we included also classification papers. Our data extraction was additionally focused on the claims of outperformance that a certain paper would put forward, and metric scores that were reported in the papers. And secondly, we derived the formula of so-called probability of false claims, and by means of extrapolating the so-called missing congruence parameters, we evaluated the stability of reporting rankings. The formula that we derived for the calculation of this probability is based on a Bayesian approach, with which we intend to estimate whether the relative ranking of methods is likely to have occurred by chance. In essence, it is the probability that the second ranked method was in fact performing equally or better than the first ranked method, given the results reported in a paper. For the classification papers that we analyzed, using our formula, we estimated that more than 86% of these papers have a high probability of false claims, and this corresponded to it being more than 5%. So on the left-hand side of the slide, you can see a heat map that is illustrating in black dots where the MICCAI 2023 papers are in the range of probabilities of false claims. And similarly, for segmentation, we estimated a high probability of false claims in 53% of the analyzed MICCAI 2023 papers. And to further analyze driving factors for a high probability of false claims, we stratified those probabilities by ranges of observed differences in performance and ranges of test set sizes. So at the intersection of the observed median difference in accuracy and median test set size, results show that demonstrating a 0.01 accuracy improvement requires a test set at least 10 times larger than the median that we observed of 500 images. While an 8 times larger test set is needed for a stable 0.01 die-score difference for segmentation papers. This is a bit more of a work in progress, but I would also like to demonstrate that we have worked also on a toolkit that would essentially assist reviewers at the first hand into assessing the stability of the outperformance claims in certain papers. So essentially the reviewer would select the type of task, add the size of the test set that they get to derive from a certain paper, and also insert the die-score values of the two top-ranked methods. And in the end, they would be obtaining some sort of a rough estimate of the probability of false claims. And in this way, we wanted to support reviewers in challenging those outperformance claims that we often get to observe in papers. And similarly, there is also a version of this toolkit for classification. And beyond that, we also have included a version that would be for the so-called researchers. So for example, you have the raw results here prior to the publication of your study or submitting your paper, and you would want to actually explore whether your method is actually highly likely to outperform its comparators. So in a way, we wanted to give access to the researchers to a toolkit that will help them into demonstrating substantiated claims of outperformance. So the take-home messages of my talk are that for proper validation for AI in biomedical imaging analysis, one should choose the right performance metrics, define their prediction problem appropriately, and report variability in model performance. And also, it's extremely important to consider further aspects that can impact the generalizability and robustness of an AI application, such as data splitting or dataset sizes. And what is evident to us, or the research group that I'm working with, is that still comprehensive guidelines for variability reporting in medical imaging AI are needed. I would like to thank all of my collaborators for this undertaking, and I'm very happy to receive your questions.